Okay, for 4.3, we actually do not need these top angles. So we're gonna go ahead and go down to where you see rotation. So a rotation is a transformation in which a figure is turned about a fixed point. Okay, that fixed point is called the center of rotation. Okay, and then the angle of rotation is formed by rays that are drawn from the center of rotation to a point and its image. Okay, and then we also really do not need that next part anymore because I skipped that now. If we have time, we'll come back to it later in the year. So, but I do want to read this bottom part. It says the figure shows above shows a 40-degree counterclockwise rotation. Rotations can be clockwise or counterclockwise. However, in this chapter, all rotations are counterclockwise unless otherwise noted. So I just want to note that most of them are counterclockwise because that'll help you kind of vision if your answer is correct or not, okay? And we'll talk about that again in a minute. So go ahead and turn the page then. We are going to skip example 1 because again, I don't do that anymore. We'll come back to it if I have time at the end of the year. So, and it's kind of the same concept here. Okay, this is, ooh, that was really ugly. Okay, this is really important. Okay, so maybe you'll put a star by there, so you can easily find it, maybe over here too, during your homework or whatever else when you're trying to figure out where those rules are at, okay? So the coordinate rules for rotations about the origin. So that is showing us if we start with AB and we rotate it 90 degrees and it becomes negative BA. For a rotation of 180, it becomes negative A, negative B. And for a rotation of 270 degrees, it becomes B, negative A, okay? If I pop back up here really quick though, it says you can rotate a figure more than 180 degrees. The diagram shows rotations of a point A at 130 degrees. Okay, so notice if I start here, I'm moving counterclockwise. Okay, that's kind of how I said you can envision where your answer should end up at. Well, 90 would probably be about right here-ish, right? So then 130 needs to be further than that. Okay, then it also shows you 220. Okay, well, you know it needs to be, this would probably be 180 right here. Well, it needs to be further than that. Okay, and then 310. So if this is the quadrant, remember that this would be, each quadrant, I guess you would say, is 90 degrees. So then you can think of that as 90, 180, and 270. And then if you kept rotating it back, again, you can see 310 is over here. Okay, and if you rotated a full 360 degrees, it would just end up right back on itself where it originally started out. Okay, so example 2, we are going to graph quadrilateral RSTU with vertices of R at 3, 1. S is at 5, 1. T is at 5, negative 3. And U is at 2, negative 1. Okay, now we are going to rotate that image 270 degrees. So the rule for 270 started at AB and it's going to go to B, negative A. So I'm going to switch the order and then I'm going to switch the sign that is on the original X value. Okay, so R prime, then is going to be at 1, -3. S prime is going to be at 1, -5. T prime will be at -3, -5. And U prime will be at -1, -2. Okay, so then I can go and graph those. R is at 1, -3. Of course, right where I wrote my U. R prime. S prime is at 1, -5. T prime is at -3, -5. And U prime is at -1, -2. Okay, again, you can see that that is the same size and shape. It has been flipped. So since it's on like this axis, this part of the axis, and I'm going counterclockwise, okay, I could think of, well, 90 degrees would end up here, right, on that axis. 180 degrees would end up on this axis over here. So then it makes sense that 270 leaves me here on this axis. So I can check my work by doing that. Okay, turn the page. Okay, graph segment RS with endpoints R at 1, -3. And S is at 2, -6. Connect those so you have a segment. Okay, and then it says, and its image after the composition. So the first one I'm going to do is a reflection in the y-axis, and then I am going to rotate it 90 degrees about the origin. Okay, so the y-axis, let me move this over here so you guys can see it better. Okay, my y-axis is running up and down here. So I'm going to reflect it first. Okay, so then, oops, R prime is going to be right here. And S prime is 1, 2 away, so 2 this way, S prime. Okay, and I'm going to write those points down where that ended up so that I can use them for my next rule. So R prime is at -1, -3. And S prime is at -2, -6. Okay, now the rule for 90 degrees about the origin is A, B is going to become -B, A. So then our double prime, remember I'm starting with my primes, I'm not going to go back. So I'm going to flip the order and switch this sign so that becomes +3, -1. And S double prime is going to become +6, -2. Okay, so 3, -1 is our double prime, and S double prime is at 6, -2. Okay, so I flipped it, and then I rotated it 90 degrees, so it's just before this one, right? And if I'm going counterclockwise, it would make sense that it's just before the next axis part there that you can see that's separating the quadrants. Okay, so there's your answers there. All right, rotational symmetry. Figure can be mapped onto itself by a rotation of 180 degrees or less. Okay, that's the big part. Okay, you only go up to 180. Okay, the center of symmetry is the center point of the figure. Okay, so for example, the figure below has rotational symmetry because a rotation of either 90 degrees or 180 degrees maps the figure onto itself. Okay, note though that a rotation of 45 degrees does not. Okay, so if I only rotated it 45 degrees, it doesn't look like my original. But if I rotated it 90 degrees counterclockwise, it looks like the original, and same thing with 180. Okay, and I stop at 180. Yes, technically I could do 270 again, and it would work, okay? And then 360 obviously is always going to land it back onto itself, but we stop whenever we get to 180. Okay, so if we're looking at these figures down here, okay, we're going to put a dot in the center. Okay, and if I think about it, so for example, if I take this point, okay, and I turn it, okay, I can only do it 180, right? So I can only do it in a straight line. Okay, am I gonna hit a point that it looks the same again? Well, yes, it does happen right there. So this is exactly 180 degrees. Okay, so the answer would be yes, 180 degrees. Okay, if you are in geometry, I expect you to know both of those things. If you are in geometry concepts, I expect you to be able to say, yes, that does have rotational symmetry. Okay, so looking at a regular octagon now. Okay, so again, I have my center point. Okay, I'm gonna draw a line kind of down the middle because there's my 180. So how many times basically can I stop and it looks the same? Well, if this point moved here, it would look the same. So there's 1, there's 2, there's 3, there's 4. Okay, so it could stop 4 times and look like itself. So the way that I think about that, well, yes, obviously it does. Then I think about 180 divided by 4, which is going to give me 45 degrees. So every 45 degrees, it looks like itself. So at 45 degrees, at 90 degrees, at 135 degrees, and at 180 degrees. Okay. Then lastly, a trapezoid. I put it here. Okay, nowhere am I going to look the same, because if I flipped it, basically if I turned it around, right, it's going to have the big side on the bottom and the smaller base there on the top. So there is none. Okay, and again, geometry concepts, I expect you to know none. I expect you to know yes and yes, but if you can figure out more than that, then that may earn you some extra credit. Okay, so it doesn't hurt to learn that as well. Okay, and that's where we are going to stop there and go ahead and do your assignment.